So you already know about linear speed, right? That's just how fast you're going. Velocity equals the change in position over the change in time. So it also kind of is distance equals rate times time, where we would solve for the rate, and we get that the rate equals distance over time. That's what this is. Velocity is the same as rate. Position is the same as kind of distance, and then time. So you already know the linear speed formula. Any questions on that? Okay. Now, when you're traveling around something, and we'll have problems like how fast is the second hand traveling? Not what's the angle it travels around, but how fast is it traveling, which does depend on the length of the radius and so forth. So if you want to know how fast it's traveling, you would need to know its change in position. Well, its change in position is going to be kind of tied in with the arc length that it surpasses as it rotates. And so here you'll see that velocity, or v equals linear speed. The s is going to be, in terms of when we're talking about circular and angular speed, the s from here is going to be like your arc length, because the distance your second hand's tip is traveling around happens to coincide with the arc length, and t is time still. And obviously arc length is r theta. That's because of the SOAR formula, right? Arc length is theta r. You with me? Okay. So if you look at this formula, this is your angular speed. Your angular speed is the change in the angle measure that you're traveling over how much time. Where, again, this, I don't know if it's a W. It's like a weirdly looking W. It might be a Greek something, I'm not sure, but we're going to call it W for lack of a better name. W is the angular speed, theta is the radian measure of an angle, and t is the time. And then I have this asterisk here, that linear speed is the product of angular speed and the radius. So how could we prove that? How could we prove that the velocity is the product between the radius and the angular speed? Using the two things that we know. Velocity is distance over time, and angular velocity, so to say, is the change in your angle over time. Stephen? Say that again. So you're kind of substituting in, right? So V, we know is the same as S over T, equals, we're keeping the R there, R over 1 times, and you're taking out the W and putting theta over T. Is that right? Okay. And, right, and then your denominators are both T, so they cancel, and then it's just your SOAR formula, which we know is true. Right? That's one way of doing it. You could substitute a bunch of different ways, but between this formula and the SOAR formula, all those substitutions kind of work out. And it really is, it's tied in with the fact that the distance we're traveling is now theta r, because it's your arc length. If you were to plug a theta r into here and get rid of your s, and velocity is supposedly just r times your w, if you just multiply this by r on both sides, rw equals r theta over t, and this is already r theta over t. So this is just a shortcut. If you know your angular speed, you can just multiply that by the radius, and that will get you to your velocity. Okay? So here's an example. A wind machine has blades that are 10 feet long. I like diagrams. 10 feet. What variable is that going to be? R equals 10. If the propeller is rotating at 4 revolutions per second, what is that? 4 revolutions per second. That might not be familiar to you. That is essentially angular speed. It gives you the change in angles or the change in rotation per unit of time. So we have an angular speed that is 4 revolutions per second. Now, what is each revolution? 2 pi. So that's 4 times 2 pi technically, which is 8 pi. So the W value is 8 pi, which is not uncommon. They'll tell you how many revolutions. You need to translate that to the number of radians, therefore, per second. So that's 8 pi radians per second. Find the linear speed. So using this shortcut here, you've got your V equals RW, you've got your R is 10, and you've got your angular speed as being 8 pi. So your velocity is 80 pi feet per second. And then obviously that doesn't really mean much to us because we have no bearing on, well, we know that's about 3, so it's somewhere around 240. So if I do 80 times pi to get the exact, 251. Does it say? We'll round to the nearest whole number. So approximately 251 feet per second is how fast the tip of that blade is moving. Okay? Just for the record, you could do this using just this. Velocity, look at kind of the correlation. It's just going to be a little bit longer. Velocity equals change in position over change in time. So if you want your velocity, the issue here is we have to figure out our change in position. So we would need our circumference, right? Yes? Yeah, we can do. Our circumference is 2 pi r, which is 20 pi. And so our total distance traveled, if it's 4 revolutions, is that circumference 4 times, right? So that's a distance of 80 pi in 1 second. Hence, kind of that. And maybe that seems easier to you, but when you'll see it on your homework, the different types of questions you're given, and then using this formula and this formula, being able to translate from angular speed to velocity. Okay? Because it's all dependent on the radius. Your linear speed is all dependent on the radius. If the radius is longer, what happens to your speed? Still does the same 4 revolutions. So your angular speed is exactly the same. Still does 4 revolutions in a second, but what moves faster? If you have a blade that's 10 feet long versus a blade that's 15 feet long, and they both do 4 full circles per second, which one's going faster? Which tip is going faster? Linearly faster. Oh, interesting. Let me rephrase that, because we seem to be a little confused. These 2 blades, I'm trying to think, they're both going to complete 4 revolutions in 1 second. So their angular speed is identical. Do you follow that? They're both doing 4 revolutions per second. Their angular speed is identical. The linear speed is faster for which one? The 15th. Because the longer the radius, the bigger the circumference, which means the bigger the distance it's traveling in that same second. right? So it's all dependent on the radius, which is kind of why to translate into linear speed, all we do is we take the angular speed and multiply it by the radius. So for the 10-foot one, it's 10 times 8 pi, and for the 15-foot one, it's 15 times 10 or times 8 pi. And obviously the 15 one is going to be larger. Does that make sense? But it's to wrapping your head around the fact that the angular speed is identical no matter how big the radius. They're both doing the same number of revolutions in a second, but the 15-foot one is covering more space, aka a larger circumference, than the smaller one. Okie doke? So just a new concept to wrap your head around with angular speed there. So the 3 questions that were omitted last night you have to do tonight. And then there was the unit circle, which, again, you spend a whole bunch of time with, so I'm going to sort of go pretty fast with this. If t is a real number and point P is some value xy, so I'm just going to put some value xy on the unit circle. When you put a point on the unit circle, maybe you remember this, maybe you were advised differently, there's different ways to teach trig. I always tell my kids, draw a terminal ray to that point and drop a right triangle. And that way SOHCAHTOA becomes your best friend. Because based on those coordinates, this leg of the triangle is x, that leg of the triangle is y, and because it's the unit circle, what's this? 1. Okay? So you get all your values. Your sine is opposite over hypotenuse, which just ends up being y. Your cosine is adjacent over hypotenuse, which just ends up being x. Hence the reason, do you remember learning that the x-coordinate was the cosine of your angle and your y-coordinate was the sine of your angle? That's all wrapped up in this SOHCAHTOA interpretation. And then your tangent, opposite over adjacent, is your y over x. You could take, if you know the point, your y-coordinate divided by your x-coordinate will give you your tangent of your angle. And then cosecant, secant, and cotangent are reciprocal functions, so you reciprocate all of those to get those. So in this first example, if you're given a point on the unit circle, give the values of the 6 trig functions at the central angle t. So the sine of t is just your y-coordinate, root 3 over 2. The cosine of t is just your x-coordinate, negative 1/2. The tangent of your t is just your y-coordinate divided by your x-coordinate, which will be what? Correct. And then your reciprocal functions, cosecant of t is going to reciprocate the root 3 over 2, but then we do still rationalize here in trig, so that's going to be 2 root 3 over 3. The secant is just going to be negative 2, and the cotangent of t is going to be negative 1 over root 3, which is going to be negative root 3 over 3. Okie doke. Okay. Now just, well, do I ask it? Do I not ask it? How much time do we have? Oh, 25 minutes? Oh, this is good. Okay, I'll go there. Just for the sake, and we're not there yet this year, but just to see, who remembers what is the reference angle that has a sine value of root 3 over 2? Okay. And based on that reference angle of 60, and, well, not based on that, but second question, based on the values of sine, cosine, and tangent, given that sine is positive, but cosine and tangent are negative, you guys remember all students take calculus? Which quadrant are we in? If sine is positive and cosine and tangent are both negative. The second, well, geez, we should have known we were in the second quadrant anyway, because we have a negative x-coordinate, which brings us left, and a positive y-coordinate, which brings us up. So we would have known that anyway. So that's a reference angle of 60 in Q2. What's the measure of the angle then? What does T equal? What is the angle that has a reference of 60 in quadrant 2? 120. That's a side note. We're not really there yet, but I'm just going to tie it all in because I know you know it, or I know it's familiar. So on this next one, find the value of the 6 trig functions at pi over 2. The book doesn't think you know your values, so let's pretend like you don't. Just based on the location of pi over 2 on the unit circle, which is where? Right here. What are the coordinates of that? What? 0, 1. So they're kind of thinking, based on those coordinates and what we just talked about with this being the cosine and that being the sine, find your 6 trig values. So your sine of t is the y coordinate 1. The cosine of t is the x coordinate 0. And the tangent of t is the y divided by the x, right? 1 divided by 0 is undefined. And aren't those in line with what I know you know, but you're not supposed to know, according to the book, about your values? The sine of 90, 1. Cosine of 90, 0. Tangent of 90, undefined. And it's all tied in with this coordinate piece as well. And then obviously if we reciprocate, we still get 1. We get undefined. And what happens when you reciprocate an undefined? 0. Something over 0 becomes 0 over something, and therefore it's 0. Okay? You know this from a couple different vantage points, but the domain of sine is negative infinity to infinity. You can plug in any angle you want, and you'll never get an undefined. So from that kind of vantage point of plugging things in, you know you can plug in anything. When you plug in something, okay, because sine is in a right triangle opposite over hypotenuse, isn't it true that the opposite side in a right triangle always has to be shorter than the hypotenuse? And therefore, if you've got a smaller number over a bigger number, you always have to be less than 1, right? And if you're a negative number, you always have to be greater than negative 1. So for those two reasons, because we can plug in and take the sine of any angle, and because when you take the sine of an angle, it's always a smaller number over a bigger number, we have to be between negative 1 and 1. There's how our domain and range are justified from the kind of algebraic thought process. Visually, you already know what that graph looks like, right? And you know it goes on left and right to infinity. So there's your unlimited domain, and your range goes from negative 1 to 1. Yes. Yes. Your cosine features are exactly the same. It's not opposite over hypotenuse, but it's adjacent over hypotenuse, and regardless, your adjacent is still a leg. A leg is always going to be shorter than the hypotenuse, is always going to create a fraction less than 1, or if it's negative, greater than negative 1, and you know what your parent graph for cosine looks like as well. Okay? So you see that oscillation back and forth between plus and minus 1. So let's talk even or odd. How do you tell if functions are even or odd? Stephen? Okay, so from the visual perspective, this is our sine curve. Is that symmetrical to the y-axis first? No, so it's not even. Is it symmetrical to the origin, meaning when I flip it upside down, is it going to look exactly the same? Yes. So that is odd. But how about algebraically, what's the test? Plug in negative x. So if I do f of negative x, and I get the sine of negative x, what do I get back? So let's go back here. if I plug in a 30-degree angle, or if x is initially a 30-degree angle, if I plug in a negative 30-degree angle, here sine was positive. What's sine of that angle going to be now down here? Negative. Same value, right? Because they both have a reference angle of 30. But this one's positive because it's in the first quadrant. This one's negative. So it got negated. Think of something that might not be in the first quadrant to start. Think of something that has a reference angle of 30 over here. What angle would that be? Reference angle of 30 in the second quadrant. 150. So the sine of 150 is positive. Do we agree? What's the sine of negative 150 then? If we plug in a negative version of that. If it's negative 150, we have to open up this way, correct? And we'll be here. Reference angle is still 30, so it's the same value, but it's in a quadrant where only tangent is positive, so again, it's going to produce a negative version of what the positive 150 produced. Do you follow that? Okay? So for that reason as well, and we could play with, different ones on that too, but for that reason, it also shows algebraically that we get the opposite of the sine of x back, and therefore that is odd. Okay? Now cosine, the graph looks a little bit different. Starts at 0, 1 and does this forever. Is that symmetrical to the y-axis? Yes. So that is even, not odd. Algebraically, though, if I do g of negative x, and I try to find the cosine of negative x, let's watch what happens. Let's do the same angles. If I start with a 30, the cosine of 30, here's negative 30. Do you see that cosine is also positive there? So they end up being the exact same value regardless. Okay? Let's take 150. The cosine of 150 is what? Plus or minus? Negative, right? It's in the sine quadrant, so it's negative. If you open up to negative 150, we're in the tangent quadrant, so cosine is still negative, right? So whether you're doing the cosine of 150 or the cosine of negative 150, you're getting your negative answer, same reference angle, so same value, you're getting the same answer both times. Do you see that? From a perspective, from the algebraic perspective, as opposed to the graph one. The graph one is easy to see. And how about tangent? Let's do tangent the algebraic way first, see if we really wrap our head around this. If I do 30, what's the cosine of negative 30 going to be? Or tangent. We're doing tangent. The tangent of 30 is positive. What's the tangent of negative 30? Negative. So it's the opposite. So just based on that one example, does it appear to be even or odd? It appears to be odd. But that's just one example. Let's try the 150. What's the tangent of 150? Positive or negative? Negative. What's the tangent of negative 150? Positive. So it's not always exactly the same. It's not, or wait. Is it always opposite? Do you think? It was positive, and then when we negated it, it was the opposite. It was negative, and then when we negated it, it was the opposite. We're not convinced. I'm not convinced. Let's pick another number. So we started with something in the first quadrant, second quadrant. Let's start with, I don't know. Let's start with 210. The tangent of 210 is what? Positive. the tangent of negative 210. So if I go around backwards, negative 210 is going to land me there. So the tangent of negative 210 is what? Negative. Do we think it's always going to be opposite? Yes, it is. So tangent is an odd function. You'll know that as soon as I graph it. Like I said, the graphing part is easier. Do you remember this? Well, that's better than I did it with my Algebra 2 kids because I didn't do it at all. So take a look at that. That's the parent graph. We'll do that again. If I flip it upside down, same thing. Right? So there's your symmetry with the origin. Trying to think here. I'm trying to separate what we know versus what I think the book is getting at by asking us these questions. With the pi over 4, I know we all know what those values are, but we're not supposed to know. So I'm trying to think what they're getting. Oh, no, I don't know if that's right either. Let me think about that. We're going to come back to those. You know your reciprocal functions. Do I need to fill those in? Why don't you all fill those in while I try to remind myself what those previous questions. Fill in those 8 trig functions. What did you say? Any ideas or guesses as to why I have the tangent and cotangent listed twice? Liam? Right. So on the first 6, I just stick to the reciprocal identities and the fact that tangent is 1 over cotangent and cotangent is a reciprocal of tangent. But there's a second way of thinking of tangent in the sine over cosine. Sine of t over cosine of t, and then the cotangent would be the reciprocal of that. So yes, they are reciprocals of each other, but almost more frequently we talk about tangent being sine over cosine and cotangent being cosine over sine. Okay? So in this example here, they give us the sine and the cosine, and they ask us to find the rest. So I'm just going to keep it all in the same order and rewrite what I know. Sine is 2/5. Cosine is root 21 over 5. So the tangent is going to come from sine divided by cosine. 2/5 divided by root 21/5, which is going to be 2 over root 21, which is going to rationalize to 2 root 21 over 21. And then your other 3 should be fairly simple. Cosecant, 5/2. Secant is 5 over root 21, which gets rationalized. And then cotangent, given that I had to rationalize this one to begin with, I'm going to flip this version of it. I'm not going to flip this version of it and have to rationalize it again. I'm going to flip this version of it so that it's already done. Okay? I'm back to this one. I think I know what they're getting at. So based on the unit circle, which we looked at yesterday, we know that pi over 4 is that perfect diagonal, yes? In fact, that terminal ray for pi over 4 lies on the line y equals x, right? So whatever the points are at the end of this, we'll say A comma B. A and B have to be equal to each other. So I'm going to drop that right triangle. And the hypotenuse is 1. And those A and B, like I said, have to be equal to each other because they're on the perfect diagonal line y equals x. So let me just call them both A for a second and do the quadratic or the Pythagorean theorem. A squared plus A squared equals 1 squared. So we get 2A squared equals 1, A squared equals 1/2, and we get A equals plus or minus, but we're in the first quadrant, so I know it's the square root of 1/2, which is root 2 over 2, once you rationalize it. So we learned then, just from knowing that that pi over 4 is on the line y equals x, that the coordinates at the end of all this are really root 2 over 2, comma root 2 over 2. Just a different presentation of it. Now, the y-coordinate is our sine value. The x-coordinate is our cosine value. So when they want the cosine of negative pi over 4, we're going to use the x-coordinate, and then we're also going to use our knowledge about whether cosine was even or odd. What was cosine? It was what? Even. So this should be equivalent to just the cosine of pi over 4, right? That's what it means to be even. Is that the original version versus the negated version should still be the same answer. And the cosine of pi over 4 is the x-coordinate, root 2 over 2. Say it again.
So it's negative pi over 4, so instead of the first one, it's 4 pi.
Right, yeah, and you just can label those points positive root 2 over 2, comma, negative root 2 over 2. Your x-coordinate would still be positive root 2 over 2. You can do that too. So what Josh is saying, and we'll do that for B, is just, if it's negative, just put it down here. And so your coordinates are just going to be still positive root 2 over 2, negative root 2 over 2. Now your tangent is your y divided by your x, so that's just negative 1. And since, if you want to kind of use that even odd piece of information, so that should be the same as the negative tangent of pi over 4, and it is, because the tangent of a regular pi over 4 would have been 1, with a negative out in front is negative 1. So just kind of a funny way of showing it. Again, them thinking, the textbook thinking that you don't know. They think this is the first time you're seeing trig, so they're showing you how these points on the unit circle kind of all make sense. What do you remember from last year about a trig identity? Sine squared plus cosine squared equals 1. Do you know that that comes from a squared plus b squared equals c squared in the unit circle? Okay. So we're just going to use that, and we know that sine is 3/5. That's the same as 9/25. Do we agree? So I'm going to subtract 9/25 from both sides. 25/25 minus 9/25 is 16/25. Square root both sides. Cosine of t equals plus or minus 4/5. Which is it? It's not both. This was always the trick and trig I remember from my junior year of high school. It's like, oh, you always got to think about these things. Which answer is correct? Is cosine positive or negative in this quadrant? If t has to be between 0 and pi over 2, what quadrant are we in? First. So is cosine positive, right? Cosine of t equals positive 4/5. If they didn't tell us that, then we would not know. We would have to say it could be either, because it was sine positive, we could have technically been in the first or the second. This further identifies what quadrant we're in. Okay? And the last thing here very quickly is period. What is the period of sine and cosine? How long does it take for them to complete a full cycle? I haven't heard it yet. Think of your graph. How long does it take for one full cycle to get in? 2 pi. That's because we're also going around the unit circle, okay? And our whole repetition won't happen until we go one full circle. So the period for sine and cosine is 2 pi. Tangent, on the other hand, has a period of pi. We will see that more when we look into the graph of it. But also, look at how the unit circle works. If you're kind of rotating through the first and second quadrants, your tangent values go from positive to negative once you're in the second quadrant. And then you restart that cycle right here, because your tangent values are positive again, followed by negative. Positive again, negative, positive, negative. And therefore, your cycle repeats every cycle of pi. So that is your period. So in this one, with sine of 9 pi over 4, since our period is 2 pi, this is going to be equivalent to, and it's almost like coming up with coterminal angles. I can subtract away 8 pi over 4, subtract away my period of 2 pi, and the sine of 9 pi over 4 will be the same as the sine of pi over 4, which was that y coordinate root 2 over 2 that we saw. Okay? Versus tangents. Tangents have a period of just pi. So this is going to be equivalent, and I can just add back 4 pi over 4. Just add back multiples of pi. So if I add back 4 pi over 4, I'm at negative pi over 4. Or I could add 4 pi over 4 in addition to that, but I would say we'll go with this one. The tangent of negative pi over 4, we already did on the front side, was negative 1. So your homework for tonight is here, and then also finishing those 3 angular speed questions from last night.